Hello everyone, and welcome back to the series on real analysis. Today we're going to be introducing a structure known as a sigma algebra, and also describe another structure known as a probability, and discuss how these two concepts kind of interconnect with one another. Now obviously probabilities are not the only use of sigma algebras, and there will be a bit of mention for measures and measure theoretic concepts. We'll get more into measure theory a little bit later and its purposes. But for now, I just want to introduce the ideas of sigma algebras and basic measures so that you sort of get used to the concept so that when we actually talk about them in a rigorous fashion later, it won't be too bad. So let's assume that omega is a non-empty set, and let's assume p omega is the power set of omega, that is the set of all subsets of that set. And let's assume that capital sigma is a subset of the power set, so a sigma algebra is just a collection of subsets of a set. Then sigma is called a sigma algebra over omega if it satisfies three properties. The first, since the sigma is a subset of all the subsets of the set, then it's possible that the empty set is or is not there, and also the entire set should be there as well, right? So the empty set and also the entire set has to be in the collection of subset of your set. Also, if E is an element of that set, then its complement, defined as omega take away E, must also be inside of that set sigma. Some people will say that sigma algebras are closed under complements, and if you have a sequence of sets, ek, where k ranges from 1 to n, or it's a countable indexed value, then the countable union of all of those sets must also be in that set sigma as well. Right, so in order for a set of subsets of sigma to be a sigma algebra over omega, empty set has to be there, the entire set has to be there, it has to be closed under complements, and it has to be closed under countable unions. So let's just go through a couple basic examples to sort of see if you can identify a set of subsets as either being a sigma algebra or not. So let's assume that omega is defined to be equal to the set 1, 2, and 3. And let's assume that somebody chooses a set of subsets of omega to be equal to the set containing the empty set, omega, and the set containing the elements 1, 2. So is this a sigma algebra over omega? Yes or no? And you might want to pause this video to sort of see if you understand this definition. So the very first property states that the empty set is in the set of subsets, and the entire set is in the set of subsets. Both of these are here, so property 1 obviously is clearly matched. The second property says that it has to be closed under complements. So obviously, if you take the empty set and complement it, you get the entire set. If you take the entire set and complement it, you get the empty set. So obviously, those two are closed under complements. So let's take a look at 1, 2. So if we take 1, 2, and we complement it with respect to omega, that's going to be the set containing 3. But notice that the set containing 3 is not an element of sigma 1. Therefore, property 2 does not satisfy for sigma algebras. Therefore, sigma 1 is not a sigma algebra over sigma. But we can easily fix this set. So for example, we can define another set of subsets, sigma 2. Let's throw empty set omega there. Let's throw 1, 2 there. And let's also throw 3 there, which is the complement of 1, 2. So obviously, P1 is satisfied and P2 is satisfied. So what about the union of all of these sets? So if we take the empty set and union it with any of those, obviously those sets are still going to be there. If we take the entire set and union it with any of those other sets, that's going to be the entire set which is there. If we take 1, 2 and union it with the empty set, it's still there. If we take 1, 2 and union it with the omega set, that's omega. If we take 1, 2 and union it with 1, 3, that's the entire set which is in there. And the same logic can go for the set containing 3 only. And you should be able to look at, for example, any 3 sets and 4 union sets for arbitrary sets and be able to argue that in a formal manner, but you should be able to see that P3 also satisfies. Therefore, what do we know? That means sigma 3 is a sigma algebra over omega. Right. So life is wonderful for sigma 2. Sigma 2. Right? So now let us define another term, which is going to be really a vague definition. We'll give a more formal definition of this concept later. But let's suppose that E is an element of sigma over omega, where sigma is a sigma algebra over omega. Then we say that E is a measurable set with respect to omega. Now, what does it mean to be measurable? And again, I'm going to give you a very slack answer for this, but this means we can define a nice function. And what do we mean by nice? Well, obviously, these functions are going to satisfy a series of formal properties, but I'm going to call this mu, and this function is called a measure, such that mu is going to take E and return to you a real number. Right? So, for example, if somebody asks you to measure your height, you're going to return with an answer. If somebody says measure the length of this rope, then you're going to return with a number as your answer. Right? So pretty much if you have a set E, an element of a sigma algebra, we say that that set is measurable, meaning we can define some function mu that maps E to R. Now let us quickly write down the definition of a very important measure that is used for probability. A measure, P, is said to be a probability measure on sigma, a sigma algebra, over omega, called a probability space if you can define P on one, if it satisfies these three properties. The first, the probability of any event is greater than or equal to 0 for all sets inside that sigma algebra. Some people will call this the non-negativity condition of probability measures. Also, if you have a sequence of sets in this set or sigma algebra sigma, sometimes people also call these E's events in omega, and EK is a sequence of disjoint sets, then the probability of the union of this sequence of disjoint sets must be equal to the sum of the probability measures of the individual events. And keep in mind, U here is a countable union of sets. And also the last property, and there's two ways you can spin this last definition, is that the probability of the entire space is equal to 1. Now, some may define the probability of the empty set to be equal to 0, and that's perfectly fine, but I find that defining the probability of the entire set being equal to 1 is a bit more of a nicer approach to define it. But you could prove one via the other, depending on your preference. So let's introduce the very first theorem for probability. And it says the following. So let's assume that EC, and this is going to be pretty much the definition always, defined to be equal to omega take away E, then the probability of E complement is equal to 1 minus the probability of E. So if you've ever taken any probability classes, this property is one of the very fundamental ones. Right? So maybe you want to pause this video and see if you can prove this on your own. Right? So it's very important to notice that for any sets that E and E complement, which is omega take away E, partition the entire space omega. And what do we mean by partitions of space? That means E union E complement is equal to the entire space, and also E intersection E complement is the empty set that is there disjoint. So that means the probability of omega is equal to the probability of E union E complement. And since these two sets are disjoint, that means that's equal to the probability of E plus the probability of E complement. And keep in mind, the probability of the entire space is equal to 1, so that means 1 is equal to the probability of E plus the probability of E complement. So if E is an element of omega, which we're assuming it is, then we can define the probability of E complement, or we can find the probability of E complement to be equal to 1 minus the probability of E, right? Provided that E is a subset of omega. And that completes the proof for the probability of complements. Right, so that's very important. The second property goes back to the comment I made about the probability of the empty set and the probability of the entire space, is that if you define the probability of the entire space to be equal to 1, which we used in this theorem, then the probability of the empty set can be found to be equal to 0. So you might want to pause the video and see if you can prove this one on your own as well. But this one's actually pretty easy. So the first thing to note is that the empty set intersection omega is equal to the empty set. They have nothing in common because the empty set has nothing in it. And also the empty set union the entire space is equal to omega. So that means you can say that the empty set and the entire space partition the entire space. Agree? So therefore, the probability of omega is equal to the probability of omega union empty. And since they're disjoint, that's going to be the probability of omega plus the probability of empty. But what do we have here? Well, we have the probability of empty, the probability of empty plus the probability of everything equals the probability of everything. But the probability of everything is equal to 1 by axiom number 3. So we have 1 is equal to 1 plus the probability of empty, and we can subtract both sides of this equation by 1 since they're all real numbers. And then we're going to have that the probability of the empty set is equal to 0, which completes the proof. All right, so that's the second more trivial proof. So now let's get into the more detailed ones. In particular, let's assume that A is a subset of B is a subset of omega. Then the probability of A will always be less than or equal to the probability of B, right? So if A is smaller than B in cardinality, then one can say that the probability of A is less than or equal to the probability of B. That is, the likelihood of A occurring is less than the likelihood of B occurring. So again, if you want to try this proof on your own, feel free to do so. Now, I'm going to go about this in a very set theoretic way. In particular, A and A complement intersection B partition the set B. And this is a very easy set theoretic thing to justify. But let me draw a little Venn diagram to sort of justify my reasoning. So if you have this bigger set B and you have a larger set A that is contained entirely within it, then what you have here is the probability or the event A. So that's the event A. And if you take A complement and intersection it with B, then what you're going to have here is this little donut region. So that's going to be A complement intersection B. So obviously, if you take A green and union it with orange, you get all of B. So therefore, if this is true, and you should be able to prove this using A as a subset of the right, and the right is a subset of the left form of equality of two sets and partitions, then we have that the probability, or A union A complement intersection B is equal to B, and also A intersection with A complement intersection B is equal to empty. So that means the probability of B, everything, is equal to the probability of A union A complement intersection B. And what is that? Well, the probability of A union A complement intersection B, since they're disjoint, is just going to be equal to the probability of A plus the probability of A complement intersection B. Now keep in mind, P is a probability measure. So P is a probability measure on omega. That means the probability of E is greater than or equal to 0 for all E within the sigma algebra over it. And also note that A complement intersection B is an element of that sigma algebra. Now, keep in mind, sigma algebras are closed under complements and they're closed under countable unions. You should be able to prove that using De Morgan's identities that sigma algebras are also going to be closed under countable intersections as well. So if A complement is there and B is there, A complement intersection B will also be there as well. And moreover, A complement intersection B is a subset of our probability space omega. So regardless of what it is, the probability of that event is greater than or equal to 0. So that means when I take away that particular object, that's going to make it result into a smaller value. So what you're going to have is the probability of B is actually going to be greater than or equal to the probability of A. Agree? Because we take away this positive value from that inequality. And if we reverse this side, then we're going to have the probability of A is less than or equal to the probability of B, which is one thing that we aim to prove in the end. All right? So that's one very important theorem. And another very fundamental theorem is the following. That is, if E is a subset of a probability space omega, then the probability of E is always between 0 and 1, inclusive of the boundaries, regardless of the event that you choose. And this sometimes people are very familiar with. So you can have a probability that's negative and can have a probability bigger than 1. So how are we going to prove this? So it's very important to recall that the empty set is a subset of every set, and every set is a subset of the set containing everything. So from the previous theorem, since we have a sequence of subsets, then the probability of the empty set will be less than or equal to the probability of E, and this can be less than or equal to the probability of the entire space. We've already proven that the probability of the empty set is 0, and axiom 3 states that the probability of the entire space is equal to 1. So therefore, from this inequality, we have that the probability of any set always belongs to this closed interval, 0, 1. And that completes the proof for that important theorem. One important theorem associated to set theory is the decomposition of the union of two sets. That is, if A and B are any two sets inside omega, you can actually partition A union B with respect to three sets. The intersection of A and B, A complement intersection with B, and A intersection with B complement. If you need a little bit of help of proving this, you can always draw a Venn diagram of two non-necessarily mutually exclusive events. The intersection obviously is going to be in the middle. A complement intersection B will be on the right, provided that the right-hand side set is B, and the left-hand side, that's going to be B complement intersection A. So therefore, blue plus green plus orange do not share any overlap in the union to the entire set, A union B. With that theorem, you should be able to easily prove that the probability of A union B is always equal to the probability of A plus the probability of B minus the probability of A intersection B for all sets. And some people will give this the name, the general sum rule for two probabilities. And it's very easy to see that if A and B are mutually exclusive, that is, they share no overlap, that is, A intersection B is equal to the empty set, then the probability of A union B will be equal to just the probability of A plus the probability of B minus the probability of the empty set, which is 0, which just gives you this particular case. And keep in mind, this is only true for mutually exclusive events. Now, you can extend this to 3 or more sets if you want, because if you want to find, for example, the probability of A union B union C, technically B union C is just a set, so you can look at this as the probability of A union X, for example. So that's going to be equal to the probability of A plus the probability of B plus the probability of C, and then minus the probability of A intersection B minus the probability of A intersection C minus the probability of B intersection C, that's a C, and then plus the probability of the third order overlap, A intersection B intersection C. And you can generalize that for more sets. For example, what about the probability of the countable union of AK? What would that be equal to? I'll leave you to generalize that representation if you want. Now, one other definition that I find is very important to define is the following. That's what we refer to as conditions. So the probability of A conditioned on B, this is usually defined as the probability of A intersection B divided by the probability of B. Keep in mind we're working in sigma algebras, so if B is there, A intersection B is definitely there, then since that's a countable intersection of events. So defining this new object is well definable in terms of the quotient of these two real numbers, provided, obviously, that the probability of B is not equal to 0. So if B cannot happen, then A condition on B is not going to be well defined. So pictorially speaking, what does a conditional probability represent? So obviously this is similar to the probability of A, but it's A conditioned on B. So if we have the entire space omega, we have A here and B here, then this region here represents the probability of A. All right, so the probability of A is just going to be equal to the size of A divided by the size of the entire probability space. So you take the area of that blue circle and divide it by the area of this rectangle, and that's going to give you the probability of A. But if B has already happened, so if B occurs, B complement cannot occur, right? So therefore, the only thing that happens if B happens has to be entirely contained within B. So everything outside of it is non-existent, right? So probability of B in this case, so here the probability of B, assuming B has already occurred, is equal to 1. Right? And then where's our little A set? So our A set was located here. But notice that part of A is missing. So this region here, which is still the only part that remains of A, so the probability of A conditioned on B, so that's that region here, can be represented with respect to the original probability space because that's still the size of the overlap divided by the size of the entire set that still remains, which in this case is equal to B. Right? So that's the pictorial representation of A conditioned on B. So from this definition, you should be able to prove several different theorems associated to conditional probabilities, but I'll leave these as exercise since they're pretty trivial. The first is the probability of B conditioned on A can be represented as the probability of B times the probability of A conditioned on B, all divided by the probability of A. And this has a very common name. This is called Bayes' rule. Bayes' rule, very good for Bayesian statistics if you know anything about that. And another very important one in the realm of probability and stochastic processes is the following. All right, so let's lay this out. So suppose EK partitions the probability space omega and let X be any event within that probability space. Then you can always find the probability of that set of interest provided that you have the individual conditionals and all information about EK. So we can find this using the probability of EK times the probability of X conditioned on EK. Right? And this has a very famous name called the law of total probability, or LTP for short. So on the pictorial representation of this, so we're going to be partitioning your space into a bunch of regions, say E1, E2, E3, and E4. And I pick any set within this realm, and I want to find the probability of it. So the probability of it is just going to be several different regions added together. So it's going to be the green plus the orange plus the black plus another color. Let's use teal, right? So that. Right? So this is going to be our event X. So the probability of x can be represented as the sum of x intersection E1, x intersection E2, x intersection E3, x intersection E4. And you should note that x intersection EK are all mutually exclusive events, and that might be able to serve as a hint on how to prove the law of total probability. Obviously, there are several more other theorems and applications of probability theory. That's more for a probability series, but I just wanted to introduce you all to the formalities of probability theory from the perspective of real analysis, which builds from very important topics known as sigma algebras and probability measures, which are just special measures in the realm of measure theory, which we'll definitely get into. So I hope you enjoyed this video, and I'll see you in the next one. Take care.